but it was all behind it.
Yes. Absolutely. That's good.
No, I think somebody's Bluetooth. Make sure you have Bluetooth up, everybody.
Okay. I was just trying to figure out where it was coming from.
Oh, I was like,
Carlos, can you hear us?
Yeah, I can hear you just fine. Can you hear me?
Yeah.
Great.
Do you want to try and share your slides already?
Sure.
To make sure it works. I don't know what I'm doing here. Okay. Thank you.
Can you see that?
Not yet. 1 second.
Yep. Yes, you can see the slides?
Yes, we can.
Mm-hmm. Great.
So here,
everything looks good.
I think people are still coming back in because we finished a little later.
Sure, just let me know when I should start.
Oh,
Right?
it's wait, sharing. It was not like this a minute ago. Not quite sure. Oh.
All right. Okay. Well, welcome everyone to this cosmology session. Our first speaker is Carlos Blanco from Princeton, and it's going remote. Please take it ahead.
Great. Thanks a lot. Hi, everyone. I'd like to tell you today about something a little bit different. I'm going to be talking about sub-GeV dark matter direct detection with nanocrystals and molecules, and I'll get around to describing what I mean by all that. But first, let me... oh, there we go. Okay. So first, let me assume that I don't need to prove to all of you that dark matter is real and necessary to make the universe work. And I'll just go ahead to telling you what I mean by sub-GeV dark matter. So by that, I don't actually mean all of the dark matter that can exist below 1 GeV. I just mean the 3 or 4 decades below about a GeV. And The reason why that's an important benchmark is because between 1 GeV and 100 TeV is where we find traditional freeze-out thermal relics. This is the WIMP parameter space, and what I mean by a WIMP is a particle that was in thermal contact with the early universe that froze out due to its annihilation cross-section or something akin to that. So we've been looking for WIMPs for a very long time, and we've gotten very, very good at looking for particles above about GeV. And after a couple of decades and a couple tons of liquid xenon, this is the state of affairs. We find ourselves with sensitivities to dark matter nucleon cross-sections of about 10 to the minus 46 square centimeters, which puts us at this line right below the Panda X blue dashed line here. And what that means is that pretty soon, within the next decade or so, the detectors are going to become so sensitive that they're going to start detecting coherent neutrino scattering. And at that point, diminishing returns means that you'll have to scale exponentially with exposure to get further down in sensitivity. And at that point, it's going to be very difficult to justify the investment in these larger and larger detectors. So for this reason, we want to look at another region of parameter space, and so we're going to move to the few decades below that, where there's plenty of well-motivated models. And there, the interaction rate for a dark matter particle can be split into 3 parts. So I don't want to get too deep in the weeds of the calculations, but this is just to say that the 3 components that fit into the calculation are eta, the mean inverse velocity, which tells you about the phase-space distribution, that's your astrophysics, the dark matter form factor, that's the parametrization of the momentum scattering amplitude of your dark matter with whatever target you have, so that's your particle physics, and finally the transition form factor. And what the transition form factor tells you is roughly how well you can absorb that momentum. It's the amplitude, the probability amplitude of absorbing momentum q, starting from some initial state psi I and going to some state psi f. So here's the whole art of detector proposals and what I'm going to spend a lot of today talking about. You have a dark matter particle coming in, traveling roughly 300 kilometers per second. It's going to impart some momentum q, and it's going to transform some state that you've prepared psi I into some state psi f, and hopefully it's going to emit a signal that you can detect. So the kinematics of the problem work out such that you have a few eV of energy available to drive your transition, and historically that means that the kinds of things that you have available to you are things like the band gaps of semiconductors or the electronic gaps in molecules and atoms. So after the initial excitation, you're left in this state psi star, and the signal usually comes from the de-excitation of such a thing. And in molecules and atoms, which is the first topic here, that equates to doing fluorescence with dark matter. Right, so what you have is a band, an absorption band, where you can absorb energy, and an emission band where the molecule is going to non-radiatively de-excite and then emit a photon. And the probability of emitting that photon and making it out of your detector is this phi FB, which is your bulk fluorescence quantum yield, and that's proportional to the overlap of those emission and absorption characteristics. So we put forward about 2 years ago a proposal and very quickly put together an experiment to look for these interactions in an organic scintillator of essentially what's benzene. And we were able to very quickly, within a month or two, have data to put down sensitivity curves on these parameter spaces. So here on the left you have something akin to a heavy mediator model, and on the right a light mediator model. And what we found is that even with this very simple off-the-shelf scintillator, within a month we could already get near striking distance of the gold standard, these silicon CCDs here, Sensei. And so we knew that using this scintillation strategy, this fluorescence strategy, was very easy, it was inexpensive, and so we wanted to do a little bit better than that. And what's more is we wanted to take advantage of both worlds, the molecular aspect of things, being able to create these liquid scintillators and these binary scintillators, and also take advantage of the fact that semiconductors are really, really good at absorbing momentum. And that's because their gaps are so small and their wave functions are the way they are. So what we found out is that there are things that are between those two worlds, and they're called quantum dots. So let me explain what a quantum dot is. In a bulk semiconductor, what you have is a lattice of atoms that extends in all directions. And the wave functions for these things are here on the lower left, right? So what that is a block wave function, which tells you about the microphysics, the local symmetries, and what's essentially a plane wave. And that's telling you that the boundary conditions are infinite. But if you take that crystal and you shrink it down and cut off the edges and make it just a few nanometers across, the only thing you've really changed are the boundary conditions. And therefore, it's only that plane wave that changes, and now it's a squeezed wave function. It's a compact wave function. Practically, that means that where you used to have these very continuous bands up to the gap edge, now you're starting to be able to resolve single states at the band edge. And the splitting of those states is set by the characteristic size of your quantum dot. And so this tunability allows you to engineer wave functions that are particularly good at picking up whatever momentum or energy you might be interested in. On the right here, this is a depiction of a quantum dot of lead sulfide, and this hair that it has around it are stabilizing ligands, that's oleic acid, and that allows you to pull these things into suspension and make essentially a liquid scintillator the way that you would with our previous experiment. Okay, so how do these things react to dark matter? Well, much the same way as other semiconductors would, right? So in silicon CCDs, you're in a situation where you excite an exciton across the band gap, and if it has enough energy, you might generate a couple of charges, and you can sequester those and read them out in a CCD. But here what's going to happen is that initial hot carrier is going to de-excite to the band edge, going to generate multiple excitons at that band edge, and those multiple excitons might emit several photons as they radiatively recombine. And we're going to look for that coincidence signal where the band edge states emit multiple photons. Okay, so we did the numerical calculations, and these are our results. So again, on the left-hand side is a heavy mediator, on the right-hand side is a light mediator. And the difference between the dashed and solid lines are what the background of the PMT is. So your photodetector has an intrinsic dark noise, and that limits the sensitivity of your experiment if you have a noisy measurement. But what we found is that, in fact, with a 10-gram-month exposure, you're essentially living in the background-free limit, where even if you reduce the background of your PMT, your signal doesn't change. And that's just a fact that you're looking for these coincident signals, and those coincident signals are very, very rare for Posonium processes. And so with this experiment that's the scale of something that can fit on a desk, you're already within striking distance of Sensei. You can perfectly characterize your experiment, and you're background free. If you scale this up by a factor of 10, which is trivial in expense, you could already do better than Sensei by about 2 orders of magnitude. So we're very excited about this. And what's more is that you get something for free. So you gain the ability to look for dark photons by absorbing them directly into the electronic states of the quantum dot. And you'll notice that there's a difference between the contours, the sensitivity contours in this figure versus the last figure. And that's because these contours are honest to goodness data. This comes from the optical spectroscopy of the quantum dot. And so all we've done is change the effect of propagator and media of the photon, and that way we're able to predict very precisely what the sensitivity of quantum dots are. And that just comes from the ability to predict the optical qualities of these nanocrystals. Okay, so what's the punchline? Well, the punchline turns out to be that the number of charge carriers, and therefore the signal that's created in a semiconductor by a scattering event or an absorption event with a dark matter particle, would be the same if the semiconductor is monolithic or if it's nanoscopically dispersed. In other words, for the dark matter, it doesn't see a quantum dot or a CCD. All it sees is a semiconductor. It doesn't really care. A semiconductor is a semiconductor. And so the whole problem boils down to what's the most effective way to engineer a signal that's very clean and background free. Okay, but what if you're interested in a situation where the dark matter is interacting with the nuclei instead of the electrons? Well, you can play a similar game where you're now starting with some initial state phi, that's a function of the nuclear coordinates, and you're going to impart some momentum q, and you're going to look for a signal, right? So traditionally, you look for the photon signal following an initial nuclear scattering event in a large atom like xenon. But in this case, the nuclei are so heavy that the kinematics just don't line up, and you're not sensitive at all to anything below about 100 MeV in dark matter mass. And so you have to, I'm sorry?
1 minute, sorry.
Okay, sure. So you have to be very clever about how you do this, and historically what you use is the Migdel effect, where an initial recoil emits an ionizing electron. But what we thought was that we could use molecules, right? So the molecular Migdel effect is the extension to this, and what we found is that there are in fact two of these things. One, which is the center of mass movement, comparable to that of the naked atom, but also there is a relative deformation effect that comes from effects beyond the Born-Oppenheimer approximation. And in that case, you suffer a penalty that's much less than that of the center of mass movement, because you only scale as 1 over the mass of the atom. And so when you put this all together, you find that even for the simplest molecules that you can think of carbon monoxide or nitrogen, you're already at parity with silicon, which raises two questions. One, is there this non-adiabatic coupling effect in silicon that's yet to be calculated? And two, can you choose optimal targets that can optimize this non-adiabatic effect? So I'm gonna skip forward a couple of slides and tell you about the most important part of this, and that's that if you look for the time-varying signal that comes from the directional detection of the dark matter wind as it changes throughout the day, you get this diurnal modulation that's of order unity compared to the mean rate, and the phase of this thing depends very sensitively on the mass of the dark matter. And to our knowledge, this is the only signal that is dependent on the mass of the dark matter, and it's a way to tease out the difference between heavy and light candidates. So I'll just stop there. And here are some acknowledgments.
Carlos, are there any questions?
Thanks for your talk. And I don't know this much about it, so maybe my question doesn't make sense. But with the xenon 1-ton experiments, it's like I thought that part of the problem is that there's not expected to be that many dark matter particles, so the probability of interaction is low. So with your quantum dots, does it mean you just would need a huge number of quantum dots to create an interaction probability? Or am I not?
Okay, good. Yeah. No, that's a good question. Let me just put it this way. The number, what we know about dark matter is the energy density. So if we're looking for dark matter candidates that are 1,000,000 times lighter, that means there's 1,000,000 times more of them. And so you don't need multiple tons of material, you need a kilogram. That's why things scale the way they do. So yes, you still need a lot of quantum dots, but they're incredibly inexpensive because the semiconductor industry is making TV panels out of them now. So it's very easy to find a kilogram of quantum dots now. Does that kind of answer your question?
Yeah, no, I hadn't thought about the fact that if the dark matter's smaller, then there's much more of them. Thanks.
Right, okay. Yep.
More questions? Anything online? Okay, great. So let's thank Carlos again. And
I need to turn it on.
yeah, if you're walking around.
Green, that's good. Okay.
Okay, great. So our next speaker is Shani Danieli from Princeton. Please take it away.
Okay. Oh, it's not sharing.
Oh,
Oh, wrong one. Sorry.
no problem.
Okay. Awesome. Hi, everyone. I'm Shani Danevi. I'm starting my third year as a Hubble Fellow at Princeton, and this is my last symposium, so I just want to say so much thank you for everything. We are the COVID Hubble Fellows, and it has been very challenging to start our postdoc during COVID, and you helped us so much, so thank you so much. So I'm going to pick up from where Carlos ended. I'm also going to talk about dark matter, but mostly its connection with dwarf galaxies. So we've heard a great introduction from Thales, why it is very important to understand dwarf galaxies, both in the context of dark matter, especially on small scales, sort of the scales of individual galaxies and galaxy groups, and also understand the interplay between the baryons and the dark matter particle. This is extremely important. If we cannot resolve this sort of two different puzzles, we cannot really say anything about either of them. So today I'm going to talk about how do we try to model this galaxy halo connection for dwarf galaxies, and especially with this new survey we call the ELV survey, led by Scott Carlson, who just graduated from Princeton. Okay, so I just want to get started, show you this snapshot from a simulation. What we see here in black is dark matter, as simulated here, and the luminous parts are shown in yellow. And what we see here is called the cosmic web. So we see this structure of filaments and clumps and subhalos and halos that host various luminous parts of the universe, mostly galaxies. And this cosmic web is really a prediction of cosmology, where dark matter just gravitates and forms the structure when it experiences gravity. And we want to try and test it, because if we have two different dark matter particles, they are going to form a completely different shape of the cosmic web, and this is something we want to test. But unfortunately, we cannot detect, maybe Carlos can, but we cannot detect dark matter directly. So instead, we use galaxies as probe for this structure. So we can look at galaxies. Can you still hear me if I move? Okay. So we can look at these galaxies and look at the distribution and try to infer the distribution of dark matter. In other words, what we really want to do is that we want to try and find a model that connects galaxies to their host dark matter halos. Okay, so if we can observe galaxies within galaxy surveys, like all of you probably know the Sloan Digital Sky Survey, we can try and use this arrow in this direction and infer how the dark matter looks like. But this relation is not super easy, so we cannot it's not a one-to-one relation. It's actually very complicated because baryons do all sort of things. Okay, they form stars, and then they have supernovae feedback, and there are sort of also dynamical effects. So this relation is actually quite complicated, and we want to try to understand this relation in order to infer these physical processes. So there has been a lot of work, and this is a really good review that I read at least every several weeks by Wexler and Tinker. So I encourage you, if you're interested, to look at this review, where there is a big range of approaches to try to model this connection, sort of starting from the more physical models, where you just put physics into the simulation and we try to observe this relation, and all the way to empirical models, where you use real data, to try and inform such relation or some galaxy halo connection model. In my work today, I'm going to focus on the more empirical side of things. So if we have a model that connects galaxies to their host dark matter halos, we can derive this very famous scaling relation. And we've heard in Ryan's talk about a different scaling relation. This is a common thing that people do in galaxy formation and evolution studies, which is the stellar to halo mass relation. So on the x-axis, we have the halo mass ranging all the way from these dwarf galaxies that we can barely see, all the way to these massive ellipticals. And on the y-axis, we have the stellar mass. Okay, so this is the stellar to halo mass relation. Here it's divided by the halo mass. And the relation shown here, so one of the key results of this research, this field, is that above some halo mass, this relation is fairly well understood, where galaxy formation is regulated, and we kind of think that we understand what's going on. But below sort of this halo mass of 10 to the 11, where the dwarf galaxy regime starts, it's not really well constrained, as you can see here. So these are just extrapolations of like many different relations that people derived with lots of data and ideas and models. We don't really understand what's going on here. Why, just to reiterate on that, why do we care about this relation? We care because if we want to understand what AGN feedback does at high masses, or we want to understand reionization, like we've heard in Thales' talk, we need to try and measure this relation from the real universe. So what ingredients go into such empirical modeling? So the first thing is we need to have dark matter subhalos. So usually what people do, they go to a simulation, and they just sort of look at the census of dark matter subhalos. So we go to simulation, we extract this information. Then we need to choose some model for how do you connect the halos to the galaxies. So often what people do, let's look at it here, they take some model where they have some parallel between the log of the stellar mass and the log of the halo mass with some slope alpha, and also allowing some scatter. So we take this model and we populate subhalos from our simulation with galaxies with some stellar mass according to some parameters alpha and sigma, okay, some random parameters. We also allow to this scatter. And then once we have these galaxies, these modeled galaxies, we can go and actually measure how the stellar mass functions, so just the count of galaxies, the function of their log stellar mass, look like, given this alpha and sigma. Okay, so we chose just alpha and sigma, but then we also have this observable from the real universe, right? We can go measure how the true stellar mass function looks like, plot it on the same plot, and just compare the two, okay? These two are not so similar, so it's probably not very likely that these alpha and sigma are real model parameters. So we calculate the likelihood, and then we repeat sort of step 2, 3, and 4 until we infer the posterior or the most likely alpha and sigma. Okay, so this is how we infer the model parameters. So thankfully, this has been done recently in the last 5 years or so for dwarf galaxies around the Milky Way. So this was enabled due to 3 different reasons. One, we now have like really nice samples of dwarf galaxies orbiting the Milky Way, thanks to the work of many, many people and surveys. The Arc Energy Survey, Sloan, of course, HSC, Penstars, and more and more and more. So we have a really nice sample of all of the dwarf galaxies that orbit the Milky Way. And also simulations can reach higher resolution, as Thales showed us. And also, we think we understand better the baryonic physics. So I just want to show 2 examples, 2 very famous examples, one from Garson Kimmel and one from Nedler. Both of them used the Milky Way or local group dwarf galaxies to constrain this relation that I showed you. So this is the parallel, right, between the stellar mass and the halo mass. And what's mostly different between the 2 is that they use different model for the dark matter subhalos. And this has been a great progress, but it also introduced a few challenges. The first one is all of these studies use only the Milky Way satellites. This is just one galaxy, one very specific galaxy. It's wonderful that and it will forever be the best data that we can get on dwarf galaxies, but we don't really know what's happening in other host galaxies, in other groups, and this scatter might actually matter quite a lot. The other 2 problems, I don't want to get into them too much. I just want to say that the Milky Way satellite number is just limited. We have just so many dwarf galaxies orbiting the Milky Way. So if we really want to try and get a better handle on how this relation look more globally, we need to look outside the Milky Way. This is hard. I talked about it in the first, or in my first symposium 2 years ago, about how difficult it is to actually find these dwarf galaxies beyond the Milky Way, just because they don't have so many stars and they are faint. Okay, they are what we call low surface brightness. But there are brilliant students like Scott who led a survey where he basically looked at data from the archives, so data from the CFHT telescope and DECOS telescope, so completely public data, and he developed tools and techniques to be able to both identify dwarf galaxies in the local volume, so everything sort of inside a sphere of 12 megaparsec from us, not only identify them, but also measure their distances, which is a huge problem in this field, using a technique I won't be talking about called surface brightness fluctuations, which I'm happy to talk about later. But what Scott did is that he practically increased our sample of satellite galaxies from 1, the Milky Way, and maybe 2, M31, to 30 groups. Okay, so from sort of 2 to 30, which one just give you a lot of dwarf galaxies that you know of, but also gives you this really nice mapping of how these satellite dwarf galaxies look like around other groups that are different. The Milky Way wasn't formed like M81, which wasn't formed like NGC 5253. So this is the survey. It's called the Exploration of Local Volume Satellites. As I said, it's actually a volume-limited sample, so it shows all of the host galaxies that are brighter than some threshold in the local volume. This is how, like a random sort of detection, a case of detecting the satellite looks like. This is the original image. You can basically see nothing. You cannot point out who is a dwarf galaxy. But if you do some processing on the image, you can point out on some candidates. Then you can go and do sort of manual or visual inspection and come up with sort of your final list of dwarf galaxies. So in total, the survey has 250 confirmed dwarf galaxies and 71 that are candidates. That means that we couldn't actually measure their accurate distance, but we know we have a probability for whether they are members of their groups or not. And this is how the stellar mass function, which is what I've shown you before, this is what we want to compare to, looks like. The Milky Way is somewhere here, and now we just have a lot of them, okay? So we have sort of this, our combined stellar mass function, and now we want to go back to what I showed you before, and we want to do this empirical modeling, okay? We want to have dark matter subhalos, we want to populate them, and we want to infer some model parameters. One more important thing is that it's not enough to look at images and find dwarf galaxies. You actually really need to understand well your selection function, okay? Because if I'm not covering the entire sort of real volume of my halo, or if I'm just not going low enough in stellar mass, it's fine. But you need to be able to say, I'm only 50% complete at 10 to the 6.2. Okay, that's really important for the modeling part. I won't get into it, but this is something that we took care of very carefully in a new paper. So here is again our flow chart of the process. Okay, so we'll go over that quickly because we already covered it. So what we did is that we chose our favorite simulation and we used the Sajjan model. That's a model developed by Jiang et al., where it's a semi-analytical model for simulating dark matter subhalos. So we create a subhalo mass function or a subhalo population that's in the local volume, where we expect will host these dwarf galaxies. Then we go to our model, okay? So we populate these subhalos with galaxies according to some model. What we did here is that not only we had the same sort of slope and scatter, but we also let the scatter grow. So if we have lower halos, we expect that the scatter will grow, which is motivated by both observations and by physics. So you populate, then you apply these observational selection functions, okay? So if I have a galaxy that has a stellar mass of 10 to the 5, I know that I'm gonna observe it at 20%. And then finally, we calculate the likelihood and we infer the parameters of the model using the galaxies from this survey, from this ELF survey, these 30 hosts satellites. And then we do MCNZ and we infer the parameters. Okay, so this is not super interesting, but this is how the posterior on the parameters of the model look like for those of you who are used to look at these parameters. But more interestingly, more important is that the black curve is our observed local volume stellar mass function. And these are the posteriors from the 1 sigma and 2 sigma confidence intervals. And you can see that the model actually, which is not that trivial, that was actually hard, but the model is very good at reproducing the observed stellar mass function. It means that we likely characterize really well our selection effect and we understand the survey. And this is what we derived for the stellar to halo mass relation. So again, this is the stellar mass on the y-axis I showed you at the beginning. And this is the halo mass. And I want to point out, it's a messy plot, but I want to point out three main results. So our derived relation is shown here in red. Okay, so this is the average relation. You see that the scatter is growing. And then compare it to various other relations that were mostly derived either using more massive galaxies that are not satellite galaxies, or using these dwarf galaxies in the Milky Way. So the first thing that we see is that our model is actually very much offset from everything that was derived so far. This is important because all of the previous studies that looked at satellite galaxies and derived this relation were actually sort of tying their high mass and to more massive galaxies that are central galaxies. And here we're talking about satellite galaxies. So this is actually sort of the first constraint where the relation is offset by a lot. And we think this is interesting. The second thing is that we find that the Bayesian inference prefers a model that has a very large scatter that actually grows. This is important because if we then want to go to our simulations, we need to put physics that will actually reproduce this scatter. Finally, we think that the scatter, so the scatter is sort of a convolution of both the scatter from sort of galaxy formation, okay, so what feedback will do, for example, or what the environment will do, but also the scatter includes sort of the host-to-host scatter. So if we might have some groups that will have more satellites here and some groups that will have more galaxies here. So this is why actually looking beyond the Milky Way and looking at other groups actually really matters. So I'm just gonna summarize real quickly. We worked on a survey called the ELF survey where we surveyed 30 Milky Way-like hosts, and we found in total 320 dwarf galaxies. They're all really well characterized. If you're interested, we can also share the data. Modeling using these galaxies, we modeled the stellar to halo mass relation for dwarf galaxies, and we found quite different results from what people find using only the Milky Way dwarf galaxies. And we hope that this model can inform simulations and the physics that people put into their simulations to resolve both what the baryons are doing, but also what's the correct dark matter model. And I don't know if I'm on time. Yeah, kind of? Okay, thanks.
Are there any questions? Just one? Just quick one.
Yeah, super interesting results. Was just wondering, the dwarf galaxy relation that you've shown here, I mean, does that sort of graph smoothly onto the more massive stellar mass halo mass relation that people have found, or do you find there are like offsets or issues that need to be dealt with between the dwarf galaxies and the massive galaxies?
Yeah, it's a great question. So you see this thing here, that's the Beruzzi relation, okay, the Beruzzi 2013 relation, which is, the most famous one, and very consistent with other relations for more massive galaxies. So we do find that they actually sort of overlap, and also that the scatter is similar. So the scatter at the high mass end is roughly like 0.1 to 0.2, right? So we do find that it's very similar. But I don't think that we should necessarily tie into the Beruzzi relations because this was constrained for central galaxies, right? So they don't have, I would expect for satellite galaxies that for a given halo mass, I would expect that the scatter will be higher and actually the stellar mass will be lower just because satellite galaxies, when they fall into the group, right, it's a little bit more, like some of the matter might get disrupted. But yeah, so it's consistent somewhat, even though we didn't force it to be tied to the high mass relation.
I'm afraid we're out of time, so if you can put your questions on Slack, please, that would be great. Thank you.
Check. One, check.
Okay.
Check.
Our next
check,
speaker
check.
is Misha Ivanov from the Institute for Advanced Study.
Is everything working? Can you hear me well? Okay, cool. Thank you. Thank you a lot, Antonello, for this nice introduction. And I would like to extend thanks to all the organizers of this meeting and the group leads. And this has been, wonderful symposium so far. And I'm really happy to be here in person. So it's my first time in person here. I'm going to talk about, all right. So I'm going to talk about fundamental physics with galaxy surveys, with the galaxy bispectrum. So I work on large-scale structure. This is the distribution of galaxies on a large cosmological scale, so of order a few hundred megaparsecs. So here you can see the example. So I'm not sure the pointer isn't working. But anyway, so here you can see the example of this distribution. And basically, we use this distribution to extract cosmology in the following way. So this distribution is obviously not random. It's a very sensitive probe of cosmological parameters. So large-scale structure is a Gaussian, is a nearly Gaussian random field. So we characterize it by means of its correlation functions, the simplest one being the two-point function, power spectrum. You see the definition over there. And basically, we just extract this two-point function from the data and fit it with some cosmological model. And this is the way how we extract cosmological parameters. In particular, we're interested in things like the density of matter, the density of baryons, the Hubble constant, and so on. But you know that the power spectrum only captures the statistical properties of a Gaussian random field, whereas the actual distribution of galaxies is far away from Gaussian. So you can see that on large scales, of course, it does look like a Gaussian distribution. So you see like random patterns of overdensities and underdensities on large enough scales. But as you start zooming in, you will start finding more complicated and nonlinear structures such as filaments, clusters, individual galaxies, and so on. So there is a wealth of non-Gaussian, nonlinear data that normally is left over and people are not using it to extract the cosmological parameters. So in order to go beyond the power spectrum and extract information, we need to, use some non-Gaussian statistics. And the simplest one such statistic is called the bispectrum. It's a three-point function of the galaxy distribution. I have already presented you the power spectrum here on the left. So basically, the bispectrum is the correlation between, let's say, three galaxies or three density fields. And the single data point of the bispectrum is the triangle, so particular configuration. And here you can see in the right part of this panel, you can see the bispectrum extracted from the data as a function of various triangles. I have presented all this, idea about non-Gaussianity and everything, but in 99% of all papers, studies devoted to large-scale structure, people just, limit ourselves with the power spectrum. And this is basically because the bispectrum data is much more, it's harder to measure and also harder to interpret and to model. And that's why it was not systematically explored before. In order to, do these kind of systematic studies, I have created a new pipeline that consists of two independent modules. So the first module is the estimation of the bispectrum from the data. So basically, we have come up with our own way to measure the bispectrum. So for experts, this way allows us to completely remove the effect of the survey window function. And then the second important ingredient is the fitting part, is the systematic theory model based on the so-called three-level and one-loop effective field theory of large-scale structure calculations. And these calculations, basically here I'm showing you the Feynman diagrams that correspond to the calculation that I have done. So having together these two parts, the measurement part and the modeling part, now we can analyze the data. And the first example we did was based on the bispectrum of the galaxies from the Baryon Acoustic Oscillation Survey. So you can see this data here on the slide. So basically we we did a joint fit of the power spectrum and the bispectrum and extracted various cosmological parameters such as H naught, the density of matter, and the clustering fluctuation amplitude, sigma 8. And here in this plot, you see the posterior distributions from this analysis. And, well, the one that you should, focus on is the red one, which is, the data, all possible, let's say, power spectrum data plus the bispectrum, and everything else are different subsets of the power spectrum likelihoods. And altogether, you see that the red contours are sharper. They are like 10% narrower than the power spectrum along contours. So on the one hand, yeah, it's noticeable. On the other hand, you might have hoped for more improvement from the bispectrum, but this improvement is kind of modest here in this situation because we have limited ourselves to the analysis of the standard cosmological models. And of course, if you go for more complicated scenarios, then you're gonna start seeing more improvement, and I will present some results later on. Let me discuss a bit this, measurement of the parameter sigma 8. So I don't know, maybe I will use this pointer. So basically, the sigma 8 is the clustering, is the amplitude of dark matter fluctuations at late times. So basically, it's the amplitude of the matter power spectrum at scale 8 h over megaparsecs. And in cosmology, people often focus on another parameter, which is called capital S8, which is basically density of matter times sigma 8. And this parameter is useful because it can be estimated independently from various large-scale structure surveys, both spectroscopic ones, like BOS and eBOS. So I'm showing you the data points over here, the results of my analysis of this data. And also it can be measured directly by the photometric data on weak lensing and galaxy clustering. And there are several surveys like KITS and DS and HSC, and I'm showing you the results over here from these surveys. And you can see that all these independent large-scale structure measurements that directly estimate this parameter S8, they point to a value around 0.75, which is in tension with the indirect prediction of the Planck cosmic microwave background radiation measurements, which sort of predicts the value around 0.85. And I think that this tension is very interesting, and it might actually hint on some new properties of dark matter. And we're trying to explore now and to understand how to, if this tension is actually real and what it means. So now let me move on to an example of a model that actually, benefits a lot from using the bispectrum. This is inflation. So inflation is the primordial accelerated expansion of our universe that took place before the Big Bang. And basically, our universe was like a balloon that was, inflated by a field in photon that was pumping up energy. And little ripples on this balloon, they correspond to gravitational fluctuations that later on have become the seeds for structure formation. And the biggest success of this inflation model is that it predicts the Gaussian distribution of the primordial fluctuations, which matches perfectly the data. And here I should say that this prediction is model independent, but the little dynamical details that are model dependent, they can be probed through the so-called primordial non-Gaussianity, just because the actual, in all these models, the actual distribution of the primordial fluctuations, of the initial conditions is different from a Gaussian by some small amount. And this is because you always have some interactions, at least due to gravity, which we know is nonlinear. And this non-Gaussianity is characterized by the skewness of the distribution, which basically equals 10 to the minus 5 times FNL. 10 to the minus 5 is the amplitude of initial fluctuations, and FNL is the amplitude of the initial bispectrum. And you can see that this effect is extremely small. So in order to sort of visualize it here on this panel, I had to crank up FNL up to 10 to the 5, which is, a crazy amount, because normally from different physical models, we expect this FNL to be order 1, and we want to detect FNL, let's say, order 1. So you see that it's a very small measurement. Well, it's a very weak effect. It's a very intricate measurement. But in principle, with the pipeline that I have created, now we can do such a measurement from the data. So as I said, we have the, bispectrum in the data, which is dominated by the nonlinearities in galaxy formation. So the total bispectrum in the data is the sum of the nonlinearities for gravity plus the primordial signal. And this primordial signal is much weaker than the late time effect. And particularly here, I'm showing you the primordial, like the background signal bispectrum over here in black, and the primordial signal here in magenta. So you see that it's like really many orders of magnitude smaller than the galaxy background. But we know this background very well, and we can compute it, to next to linear order and next to linear order, like to include the so-called one loop, two loop corrections, and so on. So basically, we can predict this background very accurately and subtract it from the data, such that we'll be able now to probe directly the primordial signal. And this is something that we have done, and we have obtained this constraint from Bose. Basically, FNL equals -30 plus -30, which I think is interesting. It's a little bit worse than, 1, than sigma, FNL 1 that we want, that they aim at. But in principle, we'll get there soon in the future. So also this measurement is somewhat worse than the best one on the market, coming from the Planck cosmic microwave background radiation, -1 plus -5. But the Planck will not improve in the future, whereas in large-scale structure, we'll get bigger surveys like Euclid very soon, and we'll beat this number soon. And I think that this analysis that we have done basically shows that this measurement is possible. So for me, it's like more a proof of principle thing. All right, so I think that I'm nearly done with my talk. So I have presented the new Tier-N pipelines to estimate and interpret the bispectrum of galaxies from spectroscopic surveys. We have applied this pipeline to the data from the Bose survey, and we have obtained new constraints on the standard model, lambda CDM. And these constraints sort of still show some tension with respect to Planck, which I think is interesting to explore in the future. And also we have obtained novel constraints on inflation, on the early physics. And I think that this is a proof of principle that such measurements can be done with large-scale structure data. And I hope that in the future, this will be one of the main targets and goals of galaxy surveys, to actually constrain the early universe. So thank you very much for your attention.
Thanks, Misha. Are there questions?
Yes, Paul?
Super naive question, but in terms of galaxy surveys, what is the trade-off between sky area and depth? How does that work in terms of constraining these models?
Yes, yeah, that's a great point. So yeah, I had a plot over here that sort of shows the both the sky area and the depth. So I think that right now, well, with Bose, the main advantage over other techniques that really get access to this three-dimensional information. So we have some significant depth. Basically, Bose goes in redshift from 0.2 to 0.7. It's very significant volume. And the sky area nominally is like less than, let's say, full sky survey, so it's like 10,000 degrees. But thanks to this depth, we actually get more information, more Fourier modes. And that's why I think that in the future also, this will be one of the key advantages of the spectroscopic surveys. So we'll get a lot of modes through these three-dimensional like spectroscopic redshifts, more than photometric surveys.
So does it scale as the total?
Basically, it scales like the redshift range, the total volume, and the total number of galaxies as well. So there are two parameters, like total volume and what we call shot noise, which is basically the number of galaxies per unit volume.
I have a naive question from a non-expert perspective. Can you go back to your power spectrum on the previous slide?
Yes.
Yeah, I don't understand why the linear theory does not match the data.
Oh, very good.
Tell me what's going on.
Thank you for this question. Yes, specifically made it look like this so that it would raise some questions. So basically, this story that, everything is like nice Gaussian here and nonlinear here, on short scales, it's also manifest when you look at the level of the power spectrum. So the power spectrum itself, it would match linear theory on large scales, but start deviating just because there would be some contributions let's say from the bispectrum and so on, to the power spectrum as well. There will be some extra correlations into it. And you see these extra correlations by like linear theory not fitting the data. And this we also need to take into account in this analysis.
So this is not like an offset that you can just like push everything up and you're like, oh, look, it matches.
Oh yeah, precisely. It's not an offset because here it matches the data quite well. And if you push it up, it will not match the data on large scales anymore.
I'm glad I bait the bait. Thank you.
Sure. Thank you for asking this question.
Okay. If there are no more questions, let's thank Misha once more. And
Great.
Yes. Okay, is this the slide board?
yes. Okay, so our next speaker is Jessica Zebrowski from the University of Chicago.
All right. Thank you for everyone for coming out. And this is the last talk of the day, so hopefully it'll be ending on a high note. So I am Jessica Ava Zebrowski, undergoing a clunky name transition right now, as I've told a lot of you, so thank you for everyone's patience. I am an incoming Einstein Fellow at the University of Chicago. And today I'm going to be talking with you about line intensity mapping with millimeter wave spectrometers, so sort of probing these unmeasured middle ages of cosmic history. So I'm going to start with this very familiar diagram for most of you, which is this artist's renditioning of the history of our universe. So off to the left, we have the Big Bang, this hot, dense point of our universe's beginning. And as you go to the right, this cone is getting bigger, which is signifying the expansion of our universe. Until you finally get to now, on the far side, right side of this picture, you see the familiar galaxies, stars, structure that many of you in this room are experts on and study today. And despite us having sort of this rough outline, this rough idea of how our universe evolved over time, there are many unsolved mysteries that cosmologists like myself get kept up at night thinking about. So for example, what is dark energy? This mysterious force driving the accelerating expansion of our universe. What mechanism drove inflation, this superluminal expansion event at the beginning of our universe that is outside of any physics we understand, but makes everything make sense about the structure that we see now? And are there relativistic species, perhaps dark matter candidates, beyond the standard model that we could probe by understanding cosmology better? And there are many collaborations measuring different parts of cosmic history trying to answer these exact questions. So at the beginning, you have cosmic microwave background experiments like my PhD experiment near and dear to my heart, the South Pole Telescope. You also have the future-looking CMBS-4, this sort of end-all, be-all of the CMB, making the best dang CMB measurement that ever will be in like 10 years from now or something. And then at the end, we have experiments studying large-scale structures such as Rubin, LSST, the dark energy survey. But we are measuring the endpoints of cosmic history, the very beginning and the very end, extremely, extremely well. However, because of all these mysteries that exist, and because we know that with 2 points you can draw a line, but with 3 points you can see if the line is changing in the middle, exploring this whole middle part of redshift space is really interesting for putting together a full picture of cosmology. And I have been recently really interested in this sort of new field of line intensity mapping that can map out these middle redshifts of cosmic history and hopefully fill in some of the picture. So line intensity mapping uses emission from atomic and molecular spectral lines from galaxies. And from this, you can make a 3D map of the galaxy distribution. So understand how the large-scale structure of our universe is changing over time in these sort of middle redshifts. Obviously, there are caveats. The first one is that you need many, many detectors on the sky to do these kind of measurements in a way where you can say anything about cosmology. And the second big caveat, and the reason this is a double-edged sword, is that this is sort of a young field. There have been no major competitive cosmological constraints made yet using line intensity mapping, which is sort of uncharted territory, which is why I'm particularly excited to sort of get my hands on this field. So what exactly is this measurement that we're making? What you are measuring is sort of this picture at the top, a low resolution intensity map, and you are making that map over multiple frequencies. So what this traces, as you can see at the bottom, is the large-scale structure in the underlying galaxy population. And the multiple frequencies give you many redshifts of that spectral line as it evolves over time. So at the end of the day, you get something like what looks to the left, this sort of evolving time cube tracing all of these lines, all of this large-scale structure in the underlying galaxy population as it's evolving over time. And this can get at some of these science goals that I was talking about at the beginning. So first of all, this sort of can tell you things about dark energy. So measuring all of these more redshifts than what we have sort of explored right now can constrain the expansion history of our universe. We got this great introduction yesterday about the Hubble Tension, and hopefully this can speak to that. And this has sort of the unique advantage to constrain models of early dark energy because you're probing the redshifts, where early emergent dark energy would be like bumping and grinding and being really, really active and turning on. The next sort of science that I think this is really interesting for is inflation. We just heard a lot about primordial non-Gaussianity, and that is something that is also really interesting to me. Basically, if you have primordial non-Gaussianity, which would be the smoking gun of multi-field inflation, that would imprint a scale-dependent bias on the matter-power spectrum. And the advantage you have here, as Paul was asking about, is that you now have this large volume of modes to constrain with line intensity mapping because you have all of this sort of redshift information. Also, if you go more into the sort of particle physics regime, you also get interesting constraints on the sum of the neutrino masses. So if you have a larger neutrino mass value, this would lead to less small-scale structure in the matter-power spectrum. And this is not a new thing. CMB has been making measurements of the sum of the neutrino masses. It has an impact on large-scale structure. But measurements like CMB makes do have degeneracy with other parameters. And making this measurement and another slice in redshift would helpfully break these degeneracies that the CMB has. And the last is sort of this, as we've talked about this morning, this dark matter, the search for new light particles is really, really hot right now as well. So any relativistic species, which would be neutrinos, sterile neutrinos, light dark matter, axions, anything you can think of, in the early universe would smear out structure within the free streaming scale. And you can see this in the power spectrum amplitude at small scales. Again, this is a measurement you can get from the CMB, but if you do line intensity mapping, you get another redshift slice, and you can hopefully break these degeneracies that the CMB has with their model. So I wish I was the first person who thought about this, and this was my idea, and I was like going to build a telescope and get it all, but I am not, and there is people working actively on this. And the sort of current state of the art for line intensity mapping is something like the experiment TIME. This is an experiment in Arizona, and you can see it pictured on the left. So this is about 50 diffraction grading spectrometers. And this could reach about 10 to the 5 spectrometer hours, which is my way of parameterizing sort of integration depth. And this, to sort of put that into context, this is giving you a power spectrum detection of these lines, but no serious cosmological constraints. And to get these cosmological constraints, what we need to do is improve instantaneous sensitivity. And to do that, and this is why I'm kind of jumping in right now, I think it's a really interesting time, is because single pixel on-chip spectrometers are now being demonstrated on sky. So SuperSpec and Decima are doing sort of their first observing runs as just single pixels. Right now they're doing sort of observations of dusty star-forming galaxies. And the thing you can see is the difference in size. So this is about 700 cubic centimeters, and SuperSpec is 1 cubic centimeter. And the thing I want you guys to take away from this is that we're finally getting to a point where you could pack enough detectors doing line intensity mapping to maybe do cosmology. So today I'm going to present to you the project that I'm going to be working on during the tenure of my Einstein Fellowship at the University of Chicago. So it'll be SPT-SLIM, the SPT Summertime Line Intensity Mapper. And the idea here is that we are going to demonstrate this line intensity mapping experiment using these on-chip millimeter wave spectrometers, which are this sort of scalable, unique technology, which is the advantage in the field that gives me hope that cosmology could one day be happening. So we're going to deploy a high-density 18-pixel dual polarization focal plane, which is about 8,000 detectors. And we'll be covering the frequency range of 120 to 180 gigahertz. And if you can see at the plot at the top, this is giving you 3 different CO lines. So CO, the J21 transition, 3.2, and 4.3. And you can see in the color what redshift you're getting them at. So overplotted in blue is the atmospheric transmission. So you can see that for most of this bandwidth, you're getting a good, clean measurement, mostly looking through the atmosphere, not being impacted by those pesky water or oxygen lines. And this is funded to be deployed in November 2023 to the South Pole. And sort of the punchline here is that if we can make a measurement of the CO power spectrum, that this is going to be a really powerful proof of this new technology and the analysis techniques you need to publish a power spectrum with this sort of scalable light intensity mapping detectors. So let's unpack the name here, the SPT Summertime Line Intensity Mapper. So SPT stands for the South Pole Telescope. The South Pole Telescope is a 10-meter off-axis Gregorian telescope at Amundsen Scott's South Pole Station. And you may know this telescope because it usually has CMB experiments inside. So it's had SPT Pole, SPT 3G, and the original SPT experiment. And what the folks at SPT have graciously let us do is for in the summer, when the weather's a little bit too bad for them to do CMB experiments, but totally fine for line intensity mapping tolerances, we're designed 2 auxiliary mirrors that we're going to pop in that I've highlighted in pink there. So they will sort of siphon off the main SPT beam, and it'll bounce off first one, off the tertiary, or the secondary, and then the tertiary, and then into our cryostat, while the SPT 3G experiment and their mirrors are still in place. So we won't be ripping out any electronics, ripping out any cameras. We can just kind of like quietly pop in our experiment and hopefully take some data while being unobtrusive to their usual observing schedule. If you take a closer look at our cryostat, at the top you can see where the light will come in into the focal plane. This is an ADR, an adiabatic demagnetization refrigerator, so it'll cool the focal plane to about 100 millikelvin. And getting, sort of down to sort of base level cold will be done by a pulse tube. Taking a little bit a closer look at our focal plane, the radiation is going to be coupled in by conical profiled horns coupled to planar orthomote transducers, OMTs, which is a very tested technology. And we'll sort of have this hexagonal close-packed array that'll then go out to our filter bank spectrometers. And each of these filter bank spectrometers, you'll see these overlapping channels in frequency space that is sort of the characteristic frequency resolution that we need to do this sort of redshift slices. And these are our science projections. So you can see here the theory curves that we are measuring. So you see that you'll have some clustering power in red, shot power in yellow, and you get this sort of total line power for each of these 3 lines at different redshifts. And even at 100 hours, we should be making detections. And we conservatively can expect a sort of 50 to 70% total observing efficiency for 4 weeks in 2023. So about 300 hours of on-target time is actually quite realistic. And the raw sensitivity of SPT SLIM should be very sufficient to detect the CO power spectra between 0.5 and redshift of 0.5 to 3 with really high significance in a single summer season. So how do we get this orders of magnitude improvement we need to get to cosmology? The answer is more detectors, right? So we'll go from a tiny packed array in the center to a bunch of horns with all the spectrometers around the edges. We'll go from an R of 300 spectrometer to about an R of 1,000 spectrometer, which seems technologically feasible to us. And we'll increase our readout multiplexing factor, which also seems reasonable given the modest increases you'd need. And this on the left can sort of see you where we're at in terms of spectrometer hours. Right now with time, things like SPT SLIM, we're sort of in the 10 to the 5 spectrometer hour regime in 2022, But this is where things get really interesting. Is if we can get one SPT-like tube, so just what I'm picturing to the right, which is a pretty modest increase, we're going to become competitive with galaxy surveys for cosmological constraints. And this to me feels really, really promising. So in summary, I'm really interested in this novel technology that's going to be probing sort of previously unmeasured parts of cosmic history. This on-chip spectrometer technology is scalable for increased sensitivity to cosmology, And a detection of the CO power spectrum with SBT SLIM will convincingly motivate analysis and hardware choices for the next generation of experiments and beyond, and paves the way for, hopefully, cosmological constraints. Thank you.
Thank you, Jessica. I already see hands up.
Thanks for that great talk. So I was wondering, there are a bunch of experiments that have gone after different parts of the spectrum to go after these dark ages, and I was wondering, so you're targeting 3 particular lines of the CO molecule. Yeah. In this case, what does the foreground look like, in the sense that when you see a spectral line from a specific direction in the sky, how do you tell the difference between one line at a different redshift and another line at a closer redshift, or what does the foreground? How do you remove that foreground contamination?
So by the foreground contamination, do you mean the fact that the lines overlap, or do you mean like literally other foregrounds, like dust in the galaxy, other astrophysical foregrounds that also emit in the microwave?
Right. I meant, let's say if you had other galaxies in the foreground, not in the redshift.
Yes. So the big advantage of the sort of frequency range that we've done, sort of the 100 gigahertz range, this is exactly where CMB measures. So CMB has had years of putting funding money into being really good at removing the astrophysical foregrounds that are getting rid of these other contaminating things that you're not looking at this cosmological signal. So we think we're basically just going to be able to use models of foregrounds in the microwave sky that already exist to subtract off the foregrounds. But the other reason that this is sort of a really slick place to be looking at is that the microwave sky is actually pretty clean. You have some dust and you have some like polarized dust, you have some dust in galaxies. This is all very well understood because of the maturity of the cosmic microwave background field.
Thanks for the great talk. Yeah, I had a question about your comparison with galaxy surveys. So at some point you said that by 2029 you'll be comparable with the galaxy surveys. So what was the point of comparison? Was it things like Euclid or DAISY or BOSS?
I mean, I'm looking at simply like how the parameters will scale and what competitive constraints we'll get. So we can talk offline. I have a nice projection of charts of like what we'll get on, FNL, what we'll get on some neutrino masses, what we'll get on different like parameters. And it's like looking at 10 to the 7th, our numbers are finally getting to the point where you're getting competitive constraints with things like BOSS, DAISY, et cetera. I'm happy to show this chart to you in more detail offline.
Thanks, Jessica, and thanks to all the speakers. If there's more questions, perhaps you can ask them on Slack. Thank you.
Thanks.
So before you go, a couple of quick announcements because we're running a bit late. We'll be taking a picture out front in just as soon as we head out and before lunch, right? That'll be our official photo tomorrow. It looks like as we walk to the restaurant, we may be able to arrange a photo from a drone. So we'll probably have 2 photos, but 2 different perspectives on the conference. There's no the coffee. There was originally going to be a coffee this afternoon because the planning was a little bit askew, and so they have. That coffee is going to be put out with the lunch. So there'll be a lot of there'll be a surfeit of food at lunch today. Feel free to take some home or for you on your travels this afternoon. Katie and I would recommend that if you're going afield, you consider going to the Inner Harbor and visiting the aquarium. That would be our primary, and then maybe go for Fells Point for the evening, which is a little bit around the edge of the harbor, a great place to go to lots of restaurants and things. If you look on on Apple Map, I just checked, it'll tell you to take the purple line down. That's the free bus. This is a free bus that runs most of the day downtown to the Inner Harbor. It's called the Charm City Circulator. There are a few lines on that. So that'll get you down for free. It's a good place to go. If you want to stay around here, we're going to the restaurant tomorrow. The Baltimore Museum of Art is really quite good. It's free. All the main collection is free, and it's got one of the best Matisse collections prior to World War II in the world. But it doesn't have the cutouts. So, but anyway, it's a very good local museum. If you don't want to go too far afield and want to do some work and just do something different for the afternoon. Okay, and now let's all go out and have our pictures taken. Who's actually got